we present Roman, the Robotic Manipulation Network. When we humans interact seamlessly with our surrounding environment in our everyday lives, most tasks we complete are sequential. In the eyes of intelligent agents, this is far from trivial. In this work, we are interested in solving complex, long-time horizon sequential tasks in robotic manipulation where demonstration data is available, in order to bring embodied intelligence on physics-based interactions closer to the capabilities exhibited by humans in our everyday lives. A promising approach is the decomposition of long and complex manipulation tasks into smaller subtasks. This in turn transforms complex long-duration sequences into more approachable problems. Following this approach, we present Roman, a hybrid hierarchical learning framework, based on a mixture of experts architecture that coordinates higher-level manipulation experts. We decompose long sequential tasks into smaller subtasks. Each subtask within our framework uses the same hybrid learning approach. Our hybrid hierarchical learning approach uses multiple learning paradigms. We blend behavioral cloning, imitation, and reinforcement learning. To combine imitation and reinforcement learning, we make use of intrinsic and extrinsic reward signals and use the proximal policy optimization as the general-purpose update rule for training all our policies. To further help the policy by warm starting it, we use behavioral cloning by performing supervised learning over the demonstration dataset. The overall learning framework achieves robust performance using a low number of demonstrations, balancing exploration and exploitation, and leading to versatility and adaptation to cases not seen in the demonstrations. The experts in our framework included pushing a switch, such as a button, pushing objects over a surface, picking and inserting an object, picking and placing, rotating opening a cabinet or door, picking and dropping items, and finally, pulling a linearly moving object such as a drawer. When these experts are fused and introduced in our hierarchical framework and managed by a gating network which we refer to as a manipulation network, long and complex robotic manipulation tasks can be solved. Here the full sequential task is shown. These include sliding opening a drawer, removing a cover from a box, rotating opening a cabinet door, picking and placing a rack, picking and inserting a vial, pushing the rack with the vial onto a conveyor belt, pushing a button to activate the conveyor belt. We trained and tested Roman in sequential tasks of increasing complexity and 3D space. Each scenario requires the activation of an additional expert, up to a total of 7 experts. Even in these high-dimensional, long sequential tasks, our results show that Roman exhibits high success rates over 90% and is robust to noise on exteroceptive observations. Additionally, we observed that Roman is able to adapt cases not seen during demonstrations. In the examples shown, we can see that during failed picking sequences, caused by the expert itself or incorrect weight assignment, Roman exhibits adaptability by re-grasping the items of interest and successfully completing the task. Another advantage of Roman's hybrid learning approach is its ability to dynamically recover from a local minima. In this example, we see how Roman's gating network quickly readapts the weight distribution during picking and inserting to recover from a local minimum. Thank you for your attention.